Why can't you do that so well?
Okay, so lecture 11.3. Well, let's review because, it's been a minute since we have been doing this stuff. So we're in chapter 11 still on frequency domain analysis, which is primarily focused on steady state frequency domain analysis, although we're going to hit a couple highlights along the way that are not steady state. And we are 3 lectures in. So the first 2 lectures were about the Fourier series and the Fourier transform. So with the Fourier series, remember, we learned that a function that is periodic can be represented as a sum of sinusoids at different frequencies and amplitudes, right? And that process of breaking down a periodic function into a sum of sinusoids, into a bunch of sinusoidal components, is called Fourier analysis. And then if you reconstruct the original signal by summing up these sinusoids, that's called Fourier synthesis. So this was the first lecture. We learned how to draw line spectra and say, okay, at this frequency component, there's this much amplitude. At this frequency component, there's that much amplitude, etc. So we learned that, and that was sort of like our introduction to the frequency domain. And then we were like, hey, what happens if we let that periodic signal have period infinity? And we were pleased to find that there was a nice mathematical object that describes exactly this, called the Fourier Transform. And instead of getting a line spectrum from the Fourier Transform, we get a continuous frequency spectrum that has components potentially at all frequencies, okay? And not just at discrete values. So it's not a line spectrum anymore, it's a continuous frequency spectrum. So that allowed us to do Fourier analysis, or frequency domain analysis or thinking, for both periodic and aperiodic signals. Okay. Now we're going to, so I mentioned that there are a lot of applications of Fourier series and Fourier transforms, and there are so many more beyond the scope of this course that we're not going to really get into in detail. But we mentioned in passing, you can solve differential equations using this. You can look at the spectrum of any signal using this way of thinking. And actually, I'll mention more about that at the end of this lecture. But what we're going to do now is we're going to explore a couple very specific new objects or new definitions using the definitions that we have looked at already. So the Fourier transform in particular is the one that we're going to be using in this lecture. So we're going to apply it now. Okay, so lecture 11.3, frequency and impulse response. So this lecture proceeds in 3 parts. First, the Fourier transform is used to derive the frequency response function, which is the last type of object we're going to use to represent systems. So what are the ones that we've really looked at in this class so far? We've looked at linear graphs. That's been one of the main ways we've represented systems. But mathematical models that we've developed are the state space representation, the input-output differential equation, the transfer function, and now finally the frequency response function is going to be the last one that we consider. So we're not going to consider any more functions, any more mathematical objects that represent systems. So these are rounds out the full repertoire that we've developed, which is actually a really pretty significant repertoire. We don't really need anything else to represent systems. That's pretty much all we need. So they're pretty useful. Great. So we'll do that. Second, we'll use the frequency response function to derive the frequency response, which is related to the frequency response function pretty directly, as you could imagine. And then the third, the frequency response for an impulse input is explored. So we're going to say, okay, what happens if we have an impulse input to our system? What is the frequency response? What does it look like? And that's an interesting thing. An interesting result pops out of that. So that's why we're going to explore that. It's not just like, oh, let's do an example. This is like a very specific exploration that's going to teach us something interesting. So, the first part, frequency response functions. Consider a dynamic system described by the input-output differential equation with the usual variables, y being the output, u being the input, coefficients, etc., etc. The nth time derivative of y and descending time derivatives of y are on the left-hand side with coefficients a. And on the right-hand side, we have b coefficients and time derivatives of u, the input. Okay, so that's our standard input-output ODE that we've come to know and love over these few months. The Fourier transform f of this equation yields something interesting. Assuming zero initial conditions, take the Fourier transform of the left-hand side, take it of the right-hand side. Remember, so if you don't recall what the properties are of a Fourier transform, which you can look them up, they're in the table, so like linearity is one that we're going to use in a moment. But also remember it's an integral definition, so anything that's true for an integral is going to be true for the Fourier transform. So that's something we can keep in mind here. And so if you have the Fourier transform of a sum, it's equal to the sum of the Fourier transform. So that's one property that we can use, and we use that right away. So this is the first equality. Second equality is here. And we have the Fourier transform of each term. Notice we've also moved the coefficients outside of the Fourier transform. We can do that because it's an integral, right? So if we have a constant, we can move it outside of the integral without affecting the value of that expression. So we have all these Fourier transforms of time derivatives. One of the Fourier transform properties in the table is that if you have a time derivative of a function and you take the Fourier transform, you get out the j omega times the Fourier transform of y of t, or also we just denote it y, capital Y. So if you do that multiple times, you have a second derivative, third derivative, etc., this j omega term just gets a power to the order of the derivative. So j omega to the n stands in for the nth time derivative of y, and so it's j omega to the n times the Fourier transform of y, capital Y, etc. The whole line, we just keep doing that. So this is the third equality here. Okay, so now we can factor out y and solve for it. So we've got y equals going to be a big fraction times u, because you can also factor out u from the right-hand side. So the fraction looks like bm j omega to the m would be times u, but we factored out u, plus bm minus 1 j omega m minus 1 plus down to b1 j omega plus b0. All that's divided by j omega to the n plus, this is the stuff that comes from the left-hand side, plus a n minus 1 j omega n minus 1 plus down to a1 j omega plus a naught. So there's our solution for y. And y is the Fourier transform of y of t. So by definition, y of omega is equal to the Fourier transform of y of t. So if you take the inverse Fourier transform of y, so if you take the inverse Fourier transform of y of omega, we get the inverse Fourier transform of the Fourier transform of y of t, which gives us the inverse Fourier transform of y of omega is just equal to y of t. So you can solve for y of t, the output as a function of time, by taking the inverse Fourier transform of this expression that we just wrote down. And it's the forced response because we assumed that the initial conditions were 0, right? So when you do that, you get the forced response. However, this is not our primary concern. So that wasn't our goal. We already know how to solve this, and we could use Laplace transforms if we wanted to. We could use the method of undetermined coefficients if we wanted to. Whatnot, what have you. But we're interested to solve for the frequency response function, h of j omega, as the ratio of the output transform y over the input transform u. So this is the definition of the frequency response function. The output over the input. And I really regret putting in the j omega here. We're going to have a whole discussion of this j omega business. Really, this is a function of omega. So like mathematically, we should be writing h of omega. And for most of the Fourier transforms, we do that. But for the frequency response function, we use this j omega business, which is just a convention, and I don't like it, but we're stuck with it kind of, because that's what the book uses, what everybody uses for the frequency response function. There will be a little bit of justification in a moment for why that is, but suffice it to say, it's just simply bad notation. So as usual, we'll use it. There is a j in there, but it doesn't mean it's a function of j omega. It's a function of omega. Omega is the variable. You wouldn't write f of 5t when it's a function of time. Just because 5 shows up with t with time everywhere, you wouldn't be like, oh yeah, no, that's a function of 5t. That's a weird thing to do. It's not really kosher math notation, but anyways, whatever. That's the sort of historical thing we're left with, so we've got it. And this is the definition of the frequency response function. So this is like output over input. Great. Well, we practically have that solved. So output over input, all we need to do is divide both sides by u, right? So if we divide both sides by u, we are left with 1120b, this expression. Note that a frequency response function can be converted to a transfer function via the substitution j omega gets replaced with s, and conversely, a transfer function can be converted to a frequency response function via the substitution s gets substituted, or j omega gets substituted for s. As in, so this is the identity here to keep in mind. This is the way we'll usually find the frequency response function. H of j omega is just equal to h of s, the transfer function, corresponding transfer function, evaluated at s equals j omega. So, it is often easiest to first derive a transfer function using any of the methods described previously, then convert this to a frequency response function. And that's actually the way that I recommend finding the frequency response function. You can do this. You can go from the the definition and use the input-output differential equation, you use the Fourier transform and all that, I would recommend just saying we have 3 different ways to derive a transfer function already. So directly from the input-output differential equation, from the state space model, and then also using impedance methods, right? Those are the 3 methods we know to derive a transfer function model. So I would recommend using one of those and then just plugging in s equals j omega. You have yourself a frequency response function. So it's pretty like easy peasy. Once you've got your transfer function, you've got your frequency response function, and vice versa. So if you've got one, you've got the other. They're really easy to convert between. Okay, so let's start doing something with this frequency response function. You know, why is it called the frequency response function is going to be kind of motivated by this next section, the frequency response. From above, we can solve for the output response y from the frequency response function by taking the inverse Fourier transform. So y of t is equal to the inverse Fourier transform of y. Great. From the definition of the frequency response function, so this is our definition here, y is just equal to hu, right? So we just plugged in y equals hu. Great. So so now we're going to have a little bit of an aside here. So we're set up here to find y of t. We want to take this a couple more steps first, though. And in order to do that, we're going to introduce the convolution theorem here. So convolution is the convolution operator is something that we talked about a little bit last time when we were talking about the Fourier transform and the Fourier transform tables. We've mentioned it in passing a couple times. I told you it comes up a lot. This is like one of the primary places it comes up. So the convolution theorem states that for 2 functions of time, h and u, if you convolve them in time and take the Fourier transform, that's equivalent to multiplying them, the Fourier transform of each of them in the frequency domain. So convolution in the time domain is equal to multiplication in the frequency domain. It's kind of the takeaway there. If we take h and u to be the time domain versions of our frequency response function and our input, then we could say that h of j omega u is equal to the Fourier transform of the convolved time domain h and u. And this is the definition of the convolution operator, 1124. So therefore, now we have this nice result that the output, or the response of the system in the time domain, is just equal to, so we know, we already have this expression from above, h of j, inverse Fourier transform of h of j omega, u of omega, but we can also represent this in the time domain, all time domain. So this expression is just equal to the convolution of h and u in the time domain, which, if you have if you want to look at from the definition of the convolution operator, the integral definition here, we have h of tau u of t minus tau d tau. So you can find the output response of the system just by convolving this mysterious h with this u, okay? And h is just defined as being the inverse Fourier transform of the frequency response function at this point. That's all it is. U is the input. So if you have the frequency response function, if you have its inverse Fourier transform, then you can find the output of the system from this expression. So this is the frequency response in terms of all time domain functions. So we got here by doing a frequency analysis. It's the frequency response of the system, but we end up with a fully time domain expression. So you can solve for the time domain response of the system using these nice Fourier transform methods. Kind of a nice little result there. We're going to use that now to find the response to a very specific input. Okay, so up here, this was for any input function. You can find what the output is, what the forced response is for that input. Now, the frequency response result includes an interesting object, h of t. We want to know, like, what is the physical significance of h other than its definition as the inverse Fourier transform of h of j omega. So this h, I mean, it kind of seems like it would be significant because capital H, the frequency response function, has a very important meaning. It's one of the main system representations. It's like the transfer function, kind of, right? So it seems like the inverse Fourier transform of it would have some significance. Like, what is it other than some function of time? What does it mean physically? How is it related to the system properties? And we can do that by, well, we can find out by putting in a very specific input here. So consider the singularity input delta of t, Dirac delta, an impulse. So this is the Dirac delta. And we've looked at this input before. It was one of our 3 singularity inputs, right? The impulse, the step, and the ramp. Those were our 3 singularity inputs. So this is one of them. The frequency response, so if we use this last expression that we derived here, is just this integral where u, instead of being just some input, is specifically the Dirac delta function, okay? And integrating over a Dirac delta function is actually pretty easy to do. There's this really nice property called the sifting property, which tells us that evaluating an integral of delta, Dirac delta, with another function effectively sifts that function and has the value of the function that the Dirac delta is multiplying at the value of time, in this case, when delta is undefined. So it's 0 everywhere except for where it's undefined, and it's got that sharp spike concept there. That's the value of time at which h is evaluated, and that's our resulting integral. So we can like do an integral pretty easily when it has a Dirac delta function in it. So the so-called sifting property yields that y of t is just equal to h of t, which is to say that h is the impulse response in the time domain. Okay? It's the frequency response when you have a Dirac delta input. So what is h of t? It's just the impulse response. Okay? So in the frequency domain, it's the frequency response function. If you take the inverse Fourier transform, it's the impulse response, which is really kind of interesting. A very interesting aspect of this result is that the frequency response function is just the Fourier transform of the impulse response. So these are 2 really interesting objects. So in the time domain, the impulse response is what happens to the system when you walk up to it and you like whack it with a hammer, right? That short, sharp input. How the system responds to that is in the Fourier domain, the frequency response function, which characterizes the whole system. It's kind of amazing that this one time domain response characterizes the entire system in the frequency domain. And that's something that we can put to great use. So,
Hey, Doctor, real quick.
yeah.
Can you just repeat that last part?
Yeah.
A lot of-
So let's look at this. So time domain and frequency domain. So we've got h of t over here. This is the impulse response in time. The frequency response over here, this is the frequency response function. So if you Fourier transform or inverse Fourier transform this, you can go back and forth, right? This characterizes the system. So it's just like the transfer function, right? Characterizes the system. And this is the response to an impulse in the time domain. It's a response to impulse. And those are just like, they seem like completely unrelated objects, right? Like how could, so what we're saying is that in a time domain, if you have some impulse, somehow that time response of the system characterizes the entire system, like for any input. Somehow it characterizes the system for any input. It gives you something that is related to the sort of foundation of the whole system. And so in the frequency domain, we have that frequency response function that is representative of the system. It's our system model. In the time domain, we have the impulse response. And so that impulse response, that response of the system to a very sharp, sudden input, somehow can be used to characterize the whole system and how it behaves, which is a very weird result. I mean, it's not something you would expect. It's not like, I wouldn't have been like, yeah, no, definitely. If you just whack the thing, it's going to tell you everything you need to know about it. But that's what this result tells us, is that if you just go up to something, I mean, you put in a sharp input pulse, right? You can characterize the whole system based on what it does, which is kind of cool. And so that's one of the things that we're going to use this for, this result. So a way to estimate via measurement the frequency response function and transfer function of a system is to input an impulse and measure and fit the response, then Fourier transform it. So the idea is in time, so like you walk up to your system and you whack it with a hammer and it does some stuff, okay? And then you're like, okay, say you took data, you like fit some function to this. You're like, okay, this is just some decaying exponential with a sinusoid at this frequency, blah, blah, blah. You fit it to some function. Then you take the Fourier transform of it. So this is h of t. You take the Fourier transform of it, and you get some frequency response function in frequency. So now you're plotting h of j omega, your frequency response function. And it might look like this or something. And this is characterizing, this is this can be essentially turned into a transfer function if you wanted to. So you could characterize the system completely, like come up with a system model by going through a process of processing data, but like if you go up and you whack something and you just process the time response of it, you could come up with a system model from that. It's pretty cool. So then you could predict what that system's going to do for any input, right? Kind of amazing that you could do that it would like give you that much information. And there are a couple assumptions that you have to make to do this. You have to assume that the system's linear. That is one thing you have to assume. So if it's a nonlinear system and you find the impulse response, that is not going to characterize the system for all inputs if it's nonlinear. So there's that to be worried about. The other question is, so how do you actually do this? Because when we measure something, we might get an analog signal here for what the input's doing, or what the output's doing, what the frequency response for an impulse looks like. But what we really do is we measure data points, right? Discrete values, we measure what h of t is. And so one thing you could do then is to fit to the data some function, okay, of time, and then do the analytic Fourier transform, etc. But more frequently what we do instead is we use what's called the discrete Fourier transform, which actually takes the data points. It's a discrete Fourier transform, and it gives us data points on this. So that would be a more common way to do it. And then there's also a faster one. There's an algorithm that can reconstruct faster, so it's called the fast Fourier transform, or FFT. So if you guys have heard of a spectrum analyzer, yeah, out there, yeah. Come on. You guys took measurements instrumentation class in the fall? You guys didn't talk about spectrum analyzers at all? Oh, come on. Oh, you guys are killing me. Mm-hmm. Oh man, we're getting to Bode plots. Don't you worry. They're right around the corner. So that's what the spectrum. That is what we call one representation of the spectrum. So a spectrum analyzer gives you a Bode plot, and what we're doing here, you can measure the time response of the system to some sharp input, and you could essentially construct a Bode plot of the system from that. Pretty cool. There are some limitations of this, so I'm going to mention this because there are different ways of measuring a transfer function or for a frequency response function. This way has some cool advantages because you can get an estimate of the entire frequency response function from one measurement, right? Just one time measurement. So if it's a system that responds quickly, like if it's a mechanical system or an electronic system, you put in an impulse, you measure the frequency response function, and bam, you measure the impulse response, you do a transform on it, and bam, you've got your Bode plot, you've got your frequency response function or your transfer function representation, like right away, like immediately, right? Pretty cool. Disadvantage though is that you got a couple things that are very much approximations, right? So one-shot measurements don't let you average things, so you'd have to do multiple shots of it anyways to get an average. Then you have to reproduce this pulse you're putting in. And remember that this direct delta function isn't something you could physically realize, this like infinitely narrow impulse. So like you'd have to figure out some way to reproduce this nice impulse. Maybe electronics wise that's a little easier, and mechanically it's a little harder to reproduce that. And you're always trying to worry about averaging your results, so it's a tricky problem to do. But if you need a really quick estimation of your system, that's a pretty cool way to do it. Now, there's a better way to get a nice high fidelity measurement of your transfer function or frequency response function. And we're going to talk about it in the next lecture. So you're probably not going to want to use this in most cases. There are some occasional cases where that might be useful. Now, there is one thing that I do want to, other thing I want to mention about this. So say you walk up to this thing and whacked it. You had the impulse response, and there was some really high frequency stuff going on. Okay. So like maybe there's like one oscillation going at this frequency, but then there's this other oscillation that's like at a higher frequency, right? And what if your sample rate is too low? Okay? If your sample rate's too low, what happens to high frequency components? You get aliasing. I knew you guys did that class. you get aliasing, and so you get that folding, right? That was one way of representing it. The aliasing is like folding of these higher frequencies down to lower frequencies. So it looks like you've got some low frequency component that's actually a high frequency. And aliasing is a big problem in discrete measurement processes, which is most of the ones that we do nowadays, discrete measurements. So if you do this type of measurement to characterize your frequency response function, if there is a high frequency response there, if there's a high frequency component that's going at a high frequency, you have to have a really high sample rate to capture that, or you're going to lose, or you're going to have some, say, like hump in your Bode plot or some aspect of your frequency response function that is, I was plotting the magnitude here, that is actually way out here, but you folded it down. So how do you mitigate that? Either have really, really high sample rates, which is hard to know when you have a high enough sample rate because everything looks good. You've just got a component down there, but it's need to just be at a higher sample rate. One thing to do is to change your sample rate and see if something moves. That's a sign that you've got aliasing. But the other thing that we can do is we can filter an analog signal, right? Before we discretize it, before we go from analog to digital, you can do a low-pass filter. If you low-pass filter it, that means that the high-frequency stuff, like this thing, is going to go away, and you aren't going to alias it down. And so that's what anti-aliasing strategies are mostly built around, is to filter out the signal before you sample. So filter it in analog before you sample and get that aliasing. Okay. Any questions about this overall, like what we're doing?
Will it have any disruption dealing with like the natural frequency of the instrumentations that you're using?
Yeah, so that's a good question. So this is what I've done here. It's like, say this was a second order mechanical system, spring mass damper thing. Maybe you've got some object that's like pretty heavy. It's got like some supports that are soft, and so they have like some flex to them. And you hit it with a hammer, and you get this sort of decay that happens. Say the motion, it starts off, it goes, and then it settles into the new value. So the frequency of that oscillation is the damped natural frequency, omega d, which is omega n times the square root of 1 minus zeta squared, right? Yeah. That's the definition, I think. So that's where the natural frequency comes in. So it's close to the natural frequency, that frequency of oscillation. If you have a higher order system, so say you have like a fourth or a sixth or an eighth order system, you can have multiple natural frequencies effectively. And so when you get to vibrations class, you're going to start thinking about that a lot more. There's going to be different modes. And so the different natural frequencies will be different modes that you have, and you can excite different modes. And that's the thing that the impulse function does, really interesting. It has all of the frequencies in it, so it excites all the frequencies. So let's actually, do you guys remember what the Fourier transform was? So function of time, function of frequency. So the Fourier transform of the Dirac delta function was? You guys remember what that was from the table?
Either the negative omega t or negative j
Or
1.
I think it's 1.
Yeah.
Am I right?
Yeah, it's 1.
Yeah. Okay. Cool. Glad I had that memory in my memory correctly. I was like, oh no, I've been always thinking it was 1. So what does that look like? What's the spectrum look like? So if we were to look at this spectrum here, so this is the Fourier transform of the Dirac delta function as a function of omega, it's 1, right? It's just constant everywhere. So that means it has all frequency components in it. It has all the frequency components, which is how it manages to characterize the system completely, is that when you input this sharp impulse, it excites all the modes of the system at once. And you guys might have seen this. What is a good example? Yeah, I think here's an example. So if you've ever had, I mean, a musical string it's like tuned to have like one mode and all that. But like if you've had like a rubber band and you've been like had it stretched tightly and somebody flicks it and you can see sort of like different shapes sort of emerge and disappear. That is effectively you're exciting multiple modes and you're seeing different modes kind of emerge there. That's what you can. That sort of like flicking the rubber band is kind of like putting an impulse into the system, and it excites all the different modes. You can think of that also like a beam that's sticking out, and you like pull it down and you let it go. And the main mode of that beam is to just oscillate up and down like this, but also another mode is going to be to bend like this, and it'll have this like S shape too that'll bend. And so you can't see them as well, but sometimes you can. It just depends on the system. You can, if it's very soft, you can sometimes see like the different shapes kind of emerge, and that like flicking or letting go of like like displacing and letting go. It's like sort of like an impulse input, and it excites all the different modes of the system at once. And that's kind of why, as a way to get an intuition on how the impulse manages to excite all the different modes of the system and manages to characterize the system completely. Even though there are some practical reasons why we don't use it to characterize the system, but in theory, if we could measure it perfectly, it would be just fine. All right? Okay. That's all I have for today. I'll see you guys Wednesday.